I want to be clear. I'm not trying to discourage anyone from taking Dr. Chen's information theory. I want students to take it because I need that class. I don't necessarily need it, but I want it to make so that I have something for him to do next quarter. That being said, that exact same class will actually be offered next fall too. It's only offered in the spring this year because he wanted to move his communication classes around to increase their enrollment, and that did not happen. So I'm going back to the old schedule because I like it better. I looked at it. Information theory should be offered next fall. That is correct. And speaking of what's offered next fall and next academic year, because some of you guys have been asking questions about that, before we get into advising in the spring quarter, so I don't want to waste too much time on this because we're already 5 minutes into class and we have yet to talk about a transistor. During advising of your, like if you're going into senior design, I'm your advisor until you graduate. So as soon as you are getting ready to enroll in senior design, which for the overwhelming majority of you should be next quarter, I will take over as your advisor if I'm not currently your advisor. Prior to advising season happening, I will come up with a list of all of the classes that I intend to offer, or the electrical engineering program intends to offer, that will count as your senior option classes as well as your directed elective classes. I will also put which classes have a corresponding graduate course, because some of you may choose to do concurrent enrollment. And I will talk about what that means when we get closer to that being a thing, but it's too early for any of you guys to register it anyway, so I'm not going to talk about it at length here. All of those classes are what I tentatively hope to have offered. Something extra may pop up. If there's not enough student interest in a particular subject, that class may get cut off of the list or whatever. The Electrical Engineering Honor Society, which is Eta Kappa Nu, do a couple of informational sessions to where effectively they're going to try to find at least one or two representatives that have taken a class and talk about what that class entails and all that kind of stuff in their experience, so that you will have an idea of what the classes look like from a student perspective, because that probably means more to you than what they look like from a professor's perspective. So all of that should happen prior to advising this upcoming spring. When we do the spring advising, it will be in person only for all of you, and it'll be 30-minute advising appointments because we have to map out your entire senior year. You don't have to stick to it, but we have to have a plan in place, because in order for you to graduate in the spring of 2025, you have to register to graduate with the College of Engineering and Science in the fall of 2024. So I need a plan in place to give to the undergraduate studies office saying, if you do this, you will complete the requirements of your graduation in the subsequent spring quarter. So by fall, we have to have a plan in place, which means during spring advising, we're making that plan, whether you like it or not. You either make the plan or I don't release you for graduation, release you for registration. And we'll actively fight anyone who does it behind my back. Just as that's it. All right, transistor stuff. So today we are going to be focused on the common emitter amplifier. I'm going to start by hitting you with something terrible, just to show you what our goal is. And then we're going to break it down into what I believe to be easily digestible blocks. You guys might disagree, but you're wrong. So the common emitter amplifier realized with an NPN BJT is going to look something like this. So up here on top, we have our supply rail VDD, nope, VCC, because this is a BJT device, sorry. This will be our collector resistance. This is our emitter resistance. Here's a resistance we're going to call R1. Here's a resistance we're going to call R2. So all of this part right here is literally just bias, right? This is nothing more than the 4 resistor bias network for an NPN BJT that we've seen before. On top of that, we are going to see some capacitor that I'm going to call CN. And this capacitor is typically very large. And by very large, I mean millifarad to microfarad range, okay? The reason why we put a large capacitor here is because we want this capacitor to look like an open circuit to DC signals and a short circuit to AC signals. Our input signal will be an AC signal. So effectively, we need to make sure that we choose a capacitor large enough such that it effectively represents no impedance to our small signal operation, okay? I'm also going to put a resistor right here that I'm going to call R sig. And this resistor right here represents the impedance of our signal. So if our signal source was thought of as a practical voltage source, this is the resistance of that practical voltage source, because our sensor that's generating our input signal might have some associated impedance as well. Over here on the left-hand side is where we would apply our input voltage as a function of time. I'm not going to keep putting as a function of time because I'm going to forget it and I'm lazy. Then over here, we'll have a capacitor called C out. This resistor will be our load. And then we're going to measure our output voltage as a function of time here. So our input signal is capacitively coupled and our output signal is capacitively coupled to the DC operating point, the transistor. The reason why we have to use capacitive coupling is because if we didn't have these capacitors here, this resistor here, RL, would appear as if it was in parallel with the resistor RC. And so it will actually influence our gain. Not having this capacitor right here means that if this signal is very small, it's effectively our input signal looks like ground. This guy right here looks like ground. And so it's going to pull our base emitter voltage to something close to ground, and it's going to turn that transistor off, which means it's not going to work as an amplifier because it'll be in the cutoff mode or very, very deep in saturation mode, since VCE would be so much larger than VBE. So capacitive coupling is absolutely required for these amplifiers, okay? We will later on use MOSFETs to do special things in order to avoid having to do capacitive coupling of signals. But that's more of an integrated circuits approach, and we're not there yet. Okay. So our ultimate goal is to analyze this entire circuit as an amplifier. So one thing that I do want to note here, common emitter amplifier. In a common emitter amplifier, the input signal is applied at the base terminal. So let me write this down. The input is applied at the base through a network as it looks like. And our output is measured at the collector. So it doesn't really matter what circuit I have. If I apply my input signal at the base and I measure my output at the collector, that we're going to treat that as a common emitter amplifier. So the emitter voltage, whatever it is common to both of these signals, which is why we call it a common emitter. When we deal with common collector amplifiers, that's the one where we're not going to take any, apply an input or measure an output or anything like that. So whichever one is the one we are not actively doing something to, that's the common node. Okay. All right, so this is what we're looking at. As it stands right now, we could actually suffer through this, but it would be really, really tedious. So what I'm going to do is I'm going to break it down into a much smaller circuit that we're going to start with. Okay. So the first thing that I want to look at is what I'm going to call the common emitter core. And that will look like either of the following two circuits. Okay. So here's VCC, some resistor, RC, here's where we apply VN. Here's where we measure V out. We're not loading anything. We're assuming our input voltage is high enough such that there's a DC component that biases this circuit the right way, all of that kind of good stuff. We actually looked at this exact circuit at the end of our last class meeting, which I guess would have been on Monday. We're going to reanalyze it, but now we're not going to be punks and we're going to include the effects of the early effect, right? All right, so this is the NPN representation. For what it's worth, over here on the right-hand side, I'll show you what the PNP would look like. So this would be VEE. RC. Here's where we take our output. Here's where we apply our input. And these will have literally the exact same small signal model. So it doesn't matter if you see it realized with an NPN transistor or a PNP transistor, they will behave identically. All right, so small signal model. What we should see is something like this. So here's my input signal VN. My base terminal. Here's my resistor R pi over which a voltage of V pi occurs. Here we have GMV pi. Because the early effect is included, we will now have this resistor R naught in play. Our emitter terminal is at AC ground. Here's our collector terminal. Here's that collector resistance RC. And here where we're measuring our output voltage. Okay. And much like we did at the end of Monday's lecture, we are going to try to figure out what our voltage gain is, what our input resistance is, and what our output resistance is. Okay. So let's start with our voltage gain. Okay. So hopefully we can all see that the resistor RC and R naught appear as if they are in parallel because they are both between the collector terminal here and ground or the emitter terminal down at the bottom. And just for sake of argument, let me put a little E there, right? So we have these two resistors in parallel, and the voltage drop across that parallel combination of resistors is our output voltage, right? So we should be able to see effectively by inspection for this relatively simple circuit that our output voltage is going to be negative GM times V pi, which is the current flowing through that parallel combination of resistors, multiplied by R naught in parallel with RC. Our input voltage, I hope we can all see by inspection, is simply the voltage V pi. Putting these two things together, we should then see that our voltage gain, AV, is simply negative GM times R naught in parallel with RC. So this is what our voltage gain is. Now let's talk about how to utilize this equation, okay? So we have two resistors that are in parallel with each other. So technically speaking, our gain is going to be the transconductance multiplied by a resistance that's smaller than either of these two, unless R naught is much, much larger than RC, in which case it's just going to look like negative GM RC, or if RC is much, much larger than R naught, then it'll look like negative GM R naught. Okay. R naught isn't something that we really have control over other than we choose the DC bias point of our system, which establishes what our collector current is and therefore establishes what R naught is depending on the early voltage of the transistor we choose. So we, other than the DC operating point, we don't really have any say over that besides just choosing a different transistor. RC is something that we choose, right? There is, however, a fundamental limit on the size of RC that we can use, because we have to remember effectively that we can never push this guy out of the forward active region if we want it to work well as an amplifier. So if I were to make a plot here, so let me draw the little circuit. So here's VCC. Here's RC, V out, V in. This is going to be a plot of, or here on the vertical axis is going to be the output voltage as a function of time. And then down here is time, right? So effectively what we've got going on is we've got some DC operating point capital V out. And then we've got an AC signal superimposed on top of it. Okay. This is what things are going to look like in an ideal case. However, let's say that this point right here represents where V out is equal to VBE. So with our current choice of where the DC part of V out is, which was established by our 4-resistor biasing network, we can see that under this particular condition, we're actually dipping into the saturation region, on the negative half cycles of our output voltage, which means we're actually going to have a distorted output signal. Instead of going that deep, it would actually look a little bit more shallow, right? We could also make a mistake on the other side of things, right? So if we pushed our DC operating points too high or too close to VCC, so let's say, for example, that VCC were up here, well, our output voltage can never get higher than VCC. So we would wind up clipping off the tops of those half cycles, which is also problematic because it's introducing distortion, right? So if we want an amplifier, chances are we want our output signal to be directly proportional to our input signal, not pretty close with a bunch of distortion added on top, right? So these are the constraints that we have to think about when we're sizing this resistor RC. If we make it too small, effectively, we're going to move our DC level of our output closer to VCC. If we make it too big, we're going to move the DC level of our output closer to VBE, and both of those are problematic. So just something that we need to consider. So the gain isn't just make RC as large as possible so that it looks like GM times R out, which is what's called the intrinsic gain of this amplifier. That's the maximum it could ever be. And we also don't want to make it so small that effectively we're running on top of the supply voltage the entire time we're trying to amplify something. Okay. So we have an understanding of the voltage gain. We also have an understanding of the limitations. Now let's look at our input resistance. So we're going to do this because this one is so easy, effectively by inspection, right? So I'm going to treat my input voltage as if it were a test voltage source. And my input resistance is then just going to be the ratio of this voltage V in to this current I in. What should that be? Somebody say it with confidence. Okay, so the input resistance of this amplifier will be the ratio of this voltage V in to this current I in. So V in divided by I in is R in. That's the input resistance. You said the input resistance will be R pi. That is correct. So even with early effects included, the input resistance is still just R pi here. So I'm just going to put R in is equal to R pi by inspection, because it really doesn't take a whole hell of a lot of math to figure that out. Now we will determine R out. Okay. So going back to my small signal model, to determine R out, I'm going to short this voltage source and apply a voltage source here at the output, which I will call V test. This is a current I test, and the ratio of that voltage V test to that current I test will be our output resistance. Okay. So when I'm determining my output resistance, I always short my input signal. So short my input terminal to ground. Okay. So much like we saw on Monday, now V pi is just 0, which means GM V pi is also 0. So all this voltage source sees is the resistance R naught in parallel with the resistance RC. So that has to be our output resistance. So we now have our 3 parameters for how our core common emitter amplifier works. So I'm trying to decide now if I want to do this amplifier with emitter degeneration, or if I want to show you guys effectively a neat trick that we're going to be using a whole hell of a lot. I'm going to go with the neat trick thing. Okay. So this is kind of an aside, but it is extremely related to what we're doing. So we analyze that teeny tiny small piece, right? We have a good understanding of how it works. I think that we have enough information to analyze this circuit. So you would be correct to assume that this looks like a huge leap in difficulty, because it does look like a huge leap in difficulty. But what we just figured out a moment ago was how this part of it works. Okay. We figured out the voltage gain, we figured out the input resistance, and we figured out the output resistance. Okay. So what I'm going to do is I'm going to draw a model of this circuit where, just to be really clear here, I'm going to make both of these capacitors short circuits with the understanding that we're working at a frequency where those capacitors look like short circuits, right? So large capacitors are going to look like short circuits, so that at a small signal level, we're just going to have this network on the input side and then this network connected to the output side. Okay, so this guy right here, this resistor, represents the input resistance of my amplifier circuit that we just looked at. I'm going to call this Rn prime. Okay, we're going to wind up finding an input resistance for our new system in terms of how it's connected to our old system. Okay. Over here, I have AV times Vn. So this is Vn. This is R out. This is V out. And we have a common ground. So I'm going to put that down here. So all of this information right here, let me put this as R out prime and AV prime. This is all the parameters of the amplifier that we just solved for. Okay. So now I need to figure out how everything else is going to be connected. So this resistor RL here is connected between the output terminal of my original amplifier and ground. So I'm going to put it right here. Now, we know what the output network looks like connected to our representation of our transistor amplifier. Now let's look at the input network, okay? So between the base terminal, which is where my input signal was applied, and ground, I have R2, but I will also have R1, since my supply voltage up there is going to look like AC ground as well. So that to me looks like R1 in parallel with R2. Anybody have a problem with that? Then between that base node and my input signal, which I'm going to call V sig this time, just so that it's not confusing, I have this resistor R sig. And here's my voltage V sig. I'm going to relabel this guy to be V sig so it's not confusing. This circuit right here is the small signal equivalent of this circuit up here. And it doesn't contain a single damn transistor. Nothing is hard. This is circuits 1 level of analysis. So let's apply circuits 1 techniques and analyze this damn thing, right? So effectively, how we're going to determine our voltage gain here is we're going to look at this as our voltage gain will be a product of V out over Vn times Vn over V sig. Let's look at what we've got. Let's start with the input side of things. What is the relationship between V sig applied over here on the left in Vn, which is the voltage applied across the input terminals of our transistor amplifier. What does that look like? It's a voltage divider. Awesome. So we could say that Vn is just going to be V sig times R1 in parallel with R2 in parallel with Rn prime divided by R sig plus R1 in parallel with R2 in parallel with Rn prime. Does anybody have any problem with that notation whatsoever? We're going to be using notation like this constant. So this is the result of my voltage divider. From this, I can very easily see that Vn over V sig is just the ratio of those resistances, right? So R1 in parallel with R2 in parallel with Rn prime over R sig plus R1 in parallel with R2 in parallel with Rn prime. Now let's figure out how V out and V in are related. Anybody have any thoughts? Another voltage divider, I'll be down. So to me, V out is going to look like AV prime Vn times RL over R out prime plus RL. And so our ratio of V out to V in looks like AV prime times RL over R out prime plus RL. Our voltage gain for our entire system is just the product of those two things, right? So we're going to have R1 in parallel with R2 in parallel with Rn prime over R sig plus R1 in parallel with R2 in parallel with Rn prime times AV RL divided by R out prime plus RL. Sorry, that should be AV prime. And now we're going to substitute in R out prime, Rn prime, and AV prime. So this is going to look like R1 in parallel with R2 in parallel with R pi times R sig plus R1 in parallel with R2 in parallel with R prime, or excuse me, R pi. Now we're going to have negative GM R naught in parallel with RC times RL divided by R naught in parallel with RC plus RL. So what I want you to do now, I want you to take a very simple, hopefully, leap of faith with me while we look at how we're analyzing. If I were to treat R naught in parallel with RC as a single resistor, I would have a resistor times RL divided by a resistor plus RL, which is what we commonly use to find the equivalent resistance between two parallel resistors. So I could take this one step further and call this negative R1 in parallel with R2 in parallel with R pi over R sig plus R1 in parallel with R2 in parallel with R pi times GM R naught in parallel with RC in parallel with R. That's our voltage gain for this fully biased transistor amplifier. Only thing that we needed to know was how the transistor part works. And then we were able to just use an equivalent circuit to figure literally everything else out about the voltage gain, which honestly skips about 3 pages of math. Pretty legit. I'm not being facetious about 3 pages of math either. I've got like 14 pages in front of me doing it the long old way that I used to do it. This is the first time I'm ever teaching it this way. It's not actually taught this way in any textbooks, but I can't figure out a reason why it shouldn't work. And everything I've done to practice it seems like it should work. So let's make it easy. Why not? Okay. All right. So with this circuit, what do we think Rn is going to be? What? What resistance does a current that's leaving the positive polarity terminal of this voltage source C on its path to ground? R sig in series with the parallel combination of these guys. That's Rn. Why does it have to be harder than? So here's our test current. We are finding the input resistance seen by the signal that we're applying to the full network. So now we're finding the input resistance of the system as a whole. So Rn is just going to look like R sig plus R1 in parallel with R2 in parallel with Rn prime, which comes out to be R sig plus R1 in parallel with R2 in parallel with R pi. Everybody okay with that? Okay. What about our output resistance? So we're looking at our output resistance just for the sake of argument, although we don't particularly need it here. See why in a moment. I'm going to put my test voltage source out here. Here's my test current source. What was that? this guy would be shorted out. So I hope that it's fairly obvious that with V6 as zeros, our input voltage here is also zero. So we have no excitation on the left-hand side of the circuit. So what does this AVVN right here look like? A short circuit, which means we're going to see RL in parallel with RL prime. There we go. We fully characterize this much larger, more difficult amplifier just by using simple circuit analysis. What? Yep. So let's look here where we literally had a dependent current source. This representation, when we turned off our input voltage, we saw that V pi was zero, which means this current was zero, which means this was an open circuit, which was why we only saw R naught in parallel with RC. Basic, literally, circuits one stuff going on. We have made electronics a joke, hopefully. Okay. And by the way, this is supposed to be the hard part of the class, like legitimately. This is the difficult stuff, but we can use simple techniques that we've been using for years to make it not that bad. Okay? So we have fully characterized how a real, practically used BJT common emitter amplifier works. We know what its input resistance is, we know what its output resistance is, we know what its voltage gain is, so we can really connect anything we want to this, and we have a good understanding of how everything is going to shake out for design purposes and all of that kind of good stuff, right? We know what the trade-offs are with trying to increase the voltage gain so that we don't accidentally push it into clipping off because we're too close to VCC, push it into saturation, clipping our negative half cycles. We've got a pretty firm grasp of this guy. What? I don't know what. So that's a concept that's typically called headroom. Okay, so we have enough information here to calculate our voltage gain, right? Purely dependent of the value of the resistors that we use to bias everything. Because if we look at this original circuit here, we've taken into account the resistance of our source, the resistance of the voltage divider leg of our 4 resistor divider network. We've taken into account the collector resistor. For this particular one, my emitter resistor is 0 because degenerating the emitter is going to increase a bit of complexity on figuring out how the transistor part works, which is what we're going to talk about next. We've got our load resistor included, all of that kind of stuff. So we know what our voltage gain is with literally everything connected to the circuit in place is, okay? We also know how to bias a network like this because we've been doing it, right? So effectively, if we know what our voltage gain is, and we know how large our input signal can be, then we know the size of the signal that's going to be superimposed on the top of the DC operating point of the output voltage. So we effectively just want to make sure that the DC operating point of the output voltage is low enough so that the highest part of our AC signal doesn't exceed VCC. And we want to make sure that the DC operating point of our output voltage is high enough to where the low parts doesn't mean that we hit saturation. That's it. So we just want a bias point somewhere in the middle, which will establish our transconductance and all of that kind of good stuff. Yep. All right, so let me take a sip of coffee. Now, let's make this first part a little bit more difficult by including the effects of emitter degeneration. because to recap here, my ultimate goal when we started this was to figure out how this circuit worked. We figured out how this circuit with this is the short circuit works. So now we got to figure out what's this guy do. All right, so common emitter core with emitter degeneration. So that's going to be something like this with a PNP BJT. So that'll be VCC, RC, here's some resistor RE. Here's our input signal. Here's our output signal. And then just in case you've seen it somewhere, here's VEE, RE, RC, VN, and VI. Okay. Once again, these will have the exact same small signal model, so they'll work identically. So I am going to walk you through this with the early effect included. I am not going to go into the nitty-gritty details of all of the algebra because it's just algebra and it's boring. Okay? I can happily upload my notes and you can see the multiple pages of algebra it takes to get from point A to part B, but effectively I'm going to set up a system of equations and then say, mashing these things together, this is the result of that, because there's really nothing to infer with the intermediate steps. It's just pure algebra, okay? All right, so our small signal model, sorry, you're texting me. I'm going to do it down here. My screen will stop wiggling on me. Yeah. So it's going to look something like this. So here's my base. Here's my resistance, R pi, over which I have my voltage, V pi. Vm, V pi. Just as a heads up, my computer's doing that weird thing where I have a lot of input lag, and so expect me to start swearing more than usual in a moment as I get frustrated. Here's RC. And here's V out. All right, so this is our small signal model. Just to be clear here, the reason why we can't just throw that input resistance, voltage gain, output resistance model that we developed earlier for the device without the generation is this emitter resistor isn't connected to our input terminals, nor is it connected to our output terminals. It was connected to where we used to have ground. So there's not an obvious way to make that model work with this. So we're going to have to go through this as its own thing. And then once we figure out how this part works, we can plug it in just like we did the other thing. Okay. All right. So let the awfulness ensue. Much like before, we're going to try to figure out what our voltage gain is first. And this is going to be a bit more of a pain in the butt than previously. Okay. So one thing that I'm going to do is I'm going to give the voltage drop across my emitter a name. Very unimaginatively, it will be VE. So to determine V out, or excuse me, to determine AV, the first thing that I'm going to do is I'm going to apply KCL at my emitter node. Okay. So I'm going to say that the currents that are flowing in, which would be the current flowing down through resistor R pi, the current provided by this dependent current source, and the current flowing down through resistor R naught, are equal to the current flowing out, which is the current flowing through resistor R. Okay. So just good old circuits one bullshit again. KCL, current flowing in equals current flowing out. Okay. So that's going to look like Vn minus VE divided by R pi plus GM V pi. Now, what's V pi? I think it's Vn minus VE by doing Kirchhoff's voltage law around that. Now I'm going to have V out minus VE divided by R naught is equal to VE over R. Simple application of Kirchhoff's current law. Any mistakes, questions, or comments? All right. Now all I'm going to do is just lump things together, right? So I'm going to separate my VNs, my VEs, and my V outs so that I have coefficients for each of those things. So manipulating this, I'm going to get Vn times 1 over R pi plus GM plus V out times 1 over R naught minus VE times 1 over R pi plus, right, the plus sign, robot. Oh, stop not responding. Okay, came back. I was about to be real pissed. Or not. Finish writing the R. Okay, there we go. One over RE plus GM. Is equal to 0. So just to be clear for the next step, what I'm doing, 1 over R pi is a conductance. GM is a conductance. So I'm going to add them like conductances, right? So conductances is going to be the inverse of how resistance is. So whenever I have 1 over resistance plus GM, what I treat that as 1 over R pi in parallel with whatever that resistance would just be 1 over GM. Same thing over here. I have this big ugly thing right here. That's, to me, I see it as the reciprocal of R pi in parallel with R naught in parallel with RE in parallel with 1 over G. That's the thing that I'm going to be doing a whole hell of a lot too. So catch on quick. So my last simplification, if you can call it that for this thing, is going to be as follows. This equation, oh, Jesus, what's happening? Is going to look like Vn over R pi in parallel with 1 over GM plus V out over R naught minus VE divided by, R pi in parallel with R naught in parallel with RE in parallel with 1 over GM is equal to 0. And this will be equation 1. And this is where I'm going to stop because we only have 7 minutes left of class and my computer is pissing me off and I want to restart. So I'll save this and we'll start.